When we were talking about k-means clustering, we made an assumption. And the assumption was that we were going to represent the classes or the clusters with a cluster center, which implicitly was assuming that the data was somehow circular or spherical or hyperspherical around the data. That was a choice. There was nothing specific about that. We could, for example, have chosen that the model is a line. So imagine this problem here. I give you a bunch of data points here, and I want you to fit, well, not one line. We know how to do that. That's least squares, total least squares, weighted least squares. But I tell you that some of the data points came from one model, which is a line, and a bunch of other data points came from another model, a different line. Or maybe there's a parabola is one model and a line is another model. Or maybe one of the models is there's a bunch of points that came from a line, and then there's just some noise in there that don't belong to either of them. In either case, let's think about how we solve this unsupervised learning problem where the model is slightly different now. It's lines instead of clusters or circles or spheres. Well, okay, it's on us to tell us what the model is. So let's say that model 1 is a line. So y sub I, so all the red points here satisfy a sub 1 xi plus b1. And notice here I've put a superscript on the a and the b, the slope and the intercept, because I'm going to have two of them, one for the red line and one for the green line. And model 2 is also a line, although it didn't have to be. And y sub I is now a2 x sub I plus b2. Don't confuse that with a squared, by the way. That's just a superscript. And the reason by the way, I put superscript here is we're eventually going to need a subscript here as well. So I understand that the notation's a little clumsy, but it'll clean up in a little bit. And so our task is very similar to what we did in k-means. We have two problems we want to solve. We want the model parameters. In this case, it's not a center, but it's a slope and an intercept. And we want to do a class assignment. We want to know which points belong to which model. Now, we have the same sort of setup that we did with k-means. If we know which data belongs to which model, estimating the model parameters a1, b1, a2, b2 is easy. Use least squares, weighted least squares, total least squares, just run it twice. Take all the red points, do least squares estimation, get a1, b1. Take all the green points, do least squares estimation, get a2, b2. Game over. We're done. We know how to do this. On the other hand, if we know the model parameters, if I tell you a1, b1, and I tell you a2, b2, well, then the model assignment should be pretty easy. How? Well, we're going to play the same game we did with k-means clustering. We're going to ask which point is closest to which line. Okay, well, how do we define closeness? Well, we have choices here. We can do the perpendicular distance. We can do the vertical distance. Let's do the vertical distance just because it's a little bit easier to parameterize. So let me define, because we're going to use this in a little bit. R sub I, the I corresponds to the ith data point. Superscript 1 corresponds to which model, model 1 or model 2, is equal to the vertical distance between the point, which has coordinates xi, yi, and what the corresponding model tells you the point should be. This should sound very familiar. This is how we derive least squares, weighted least squares estimation. So the model tells me that point xi, yi should be at point a sup x, k rather, times xi plus b sup k, the kth model parameters. And I'm going to just take the absolute value or the square or whatever it is. Let's worry about that later. And so if a point is closer to line 1, it belongs to line 1. If the point is closer to line 2, it belongs to line 2. So that's sort of similar to what we did with the clustering. We just have a different measure of closeness. It's not the Euclidean distance. It is the vertical distance. Now, so we have the same problem. We've set it up exactly the same way. If I tell you the model assignment, cluster assignment, class assignment is easy. If I tell you class assignment, model estimation is easy. This new algorithm called expectation maximization, and by the way, we could have run k-means on exactly this. We're going to introduce a new idea with one little twist, but a really important twist on it. Expectation maximization, EM, is a two-step algorithm that iteratively estimates model parameters and model assignment, exactly like k-means. Except there's one new twist to this, which is that unlike k-means, the class assignment is probabilistic. So what I mean by that is we are not just going to say this point belongs to this line and this point here belongs to this line. What we're going to say is this point belongs to this line with probability p, and it belongs to the other line, the other class with probability 1 minus p, because there's only 2 classes here. Now, why is that useful to have a probabilistic assignment? Well, let's go right to that intersection of those 2 lines. If I gave you a point right at that intersection, does it belong to class 1 or class 2, red line or green line? I don't know, it's completely ill-defined. We have no idea. So points that are ambiguous, you would like to maybe say, well, I'm not really sure what the class assignment is. On the other hand, I'm fairly sure that points up here and points over here really do belong to that because they're very clearly and unambiguously there. So this probabilistic component is, you can think of EM as a probabilistic version of k-means. We have the same problem. We have a bunch of data in some arbitrary dimensional space. We have a model. I've made the model lines instead of clusters just so you could see that there was nothing special about the clusters, but I could have done this with clusters as well. And now what we're going to do is we're going to do this iterative model estimation, class assignment, repeat, 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 but we're going to introduce this new part, which is a probabilistic class assignment, which makes things a little bit more complicated, but not too much.